Alright, another video lesson. So this is some solutions to additional torque and statics practice. You should do these on your own and then check your solutions by watching this. So, number one, what's the reading in the spring scale? We have a situation with a beam or something, mass of 10 kilograms, length of 1 meter, spring scale attached 90 centimeters from the rotation point. So basically, we're going to equate the torques. Torque is provided by the spring scale like this, and torque is provided by the center of mass like this. So if the thing's not moving, which it isn't, it means that the torque around this point of rotation will be equal in both directions. So I chose this as the point of rotation. Hopefully that's obvious. If it's not, you can choose the point of rotation as anything. But if I had, say, chosen this as the point of rotation, then we would have to take into consideration the torque, the upward torque provided by the wall, and that's not what we're interested in. So let's not do that. Oops. What happened there? Wait. Back. Oh, great. Alright. Cool. So, it goes like this. We're going to say that the torque provided by the center of mass is the force. So first of all, torque is force times radius, and it's the force component of force that is perpendicular to the radius. In this case, they are perpendicular, so this would be the radius, this would be the force. The force is weight, so it would be mass times gravity times the radius, which is half a meter. We can assume that the center of mass is in the middle, or center, of the beam here. Because that torque is going downward, we're going to say it's equal to the torque upward, which will be force times radius, which is 0.9. Okay. No problemo here. So, calculator, let's see, 100, oh look, this is going to be 50, and this is divided by 0.9 equals force. Looks like, so hopefully you're doing this, or you've already done this, or else I would pause and give you time to, but it looks like something like this, newtons, and I should be more specific in the question about significant figures, like is that 10 or 10.0 or whatever, so don't stress about that right now, but looks like this would be the reading in the scale. And so in general, spring scales in physics class would be measured in newtons, and so that sounds good. So a way that you can sort of think, hey, does this make sense, is by looking at the situation and thinking about it. You think, okay, if 100 newtons is pulling down here, how much, and just picture yourself pulling up, okay, would it be more or less than the weight? Hopefully it makes sense that it's less than the weight, so I'm going to go with this answer and call it good, meaning it looks like it's correct. Number two, looks like a similar situation, but different, if that makes any sense. Let's see if we can erase. No. Alright, so I'm going to make some white writing on that thing here. Hey. Alright. And there it goes. Okay, so we need to make this pen tip more narrow. So we have a, let's call this, let's see if this works. We're going to call this the point of rotation. We can say point of rotation, and we have in the center of mass a force downward, and we kind of assume that this spring scale will be upward and this spring scale will be upward. If we were to, let's say, solve for F, and get a negative value, we'd say, okay, this is pointing downward, but I don't think that's going to be the case. So, before we proceed, let us write in the force and see what we can say. We're going to call this F1, and we're going to call this F2. If they were hanging equal distances from the center of mass, we could assume they are the same, but they are not. Darn. And this would be the weight. So weight, and that's going to be mg. It looks like 10 kilograms, so I'm going to do mg and a nice round number. Thanks, T. No problem. Got your back. 100 newtons as the force applied at the center of mass. Notice how we have, what are we noticing? 10, 40, 50, 30. Okay, so the total distance is 80. We know that the radius for this force is going to be 10. The radius for the center of mass is the center of 80, so 40. And the radius for this guy is 50. Okay, so let's write that out and see if it works. To me, it looks like we're going to have two variables. Dun, 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 dun. So we're going to have to come up with some other relationship between these two. Hopefully you recognize that they both, together they support this weight. So we know that F1 plus F2 has to equal 100 newtons. Nice. Let's write that down. F1 plus F2 equals 100 newtons. That's a 100, even though it doesn't look like it. Okay, so we are equating the torques, and what do we say? F1 times the radius, which is 10 centimeters. Notice I'm putting in meters. This is a times. And I'm going to say plus, because these are torques in the counterclockwise direction. F2 times, and the radius for F2 we figured was 50 centimeters, so 0.5 meters, and that is equal to the force due to gravity acting at the center of mass, which is weight, 100 newtons, times the radius, which was half the length of the thing, whatever that thing is, so that was 40 centimeters. The center of mass is in the center of the thing. Okay, so I'll just do a little simplifying and then see if we can do a little substituting or something. So we have 0.1 F1 plus 0.5 F2 equals 40. Okay. So given this formula and given this formula, we can substitute, no problemo. I am running out of space, so I'm going to zoom and see what we can do here. Much better. Okay. So, given the equation that was up there, which was F1 plus F2 equals 100. We could say F1 equals 100 minus F2. And we're going to substitute this in here. So we have 0.1, 100 minus F2 plus 0.5 F2 equals 40. Moving on. I'm going to distribute and combine like terms and do some subtracting, dividing, yada yada. Ooh, good thing I didn't work this out beforehand. So 0.1 times 100 is 10 minus 0.1 F2 plus 0.5. Oh, this doesn't look bad. That's a 0.5. by the way, F2 equals 40. We subtract 10 and combine like terms. Easy breezy. 0.4 F2 equals not 10. Nope. No. Ooh, I did not mean to do that. Dang. Oh, there we go. Nice. Good work, Torville. Okay, where was I? Right. 0.4 F2 equals, there we go, 30. And then dividing 30 by 0.4 yields that F2 is, oh, this is so fun, 75 newtons. Okay, so before we put in any more work, let's check ourselves. Does that make sense? In eyeballing the situation, this is sort of out towards the end, whereas this is much closer to the center, so this checks out. This looks good. If the whole thing weighs 100 newtons, 75 newtons here, so we can kind of just assume, well, sure, we know that F1 will be 25 newtons because together they support that weight. Or if you're a formula kind of person, well, we're just plugging in here. So zoom back in, get this answer in here. If F2 equals 75 newtons, well then F1 equals 25 newtons from this here formula. Alright, moving on. If you're still awake, oh my gosh. You know what, I'm going to do this in part 2 just so that you don't fall asleep and I don't run out of memory.